This lesson has been developed in the framework of SCILED project. Module 3, Footwear Design Engineering, Unit 3, Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lecture 3.1. Finite Element Analysis, FEA, in Footwear Design Engineering. Introduction. The comfort and performance of a footwear are interrelated concepts. It is preferable to consider overall the functionality, performance, form, and fit, also known as 3F. Vink et al. Also believe that comfort includes convenience issues that arise after using a product because the appearance of several physical, physiological and psychological aspects is lagging the end of the use of goods and services. Another typical example of physiological aspects which appear after the end of the use of a product is the development of callus as a result of pressure points and friction within the footwear. Comfort in product design.
In the modern practice of designing clothing and footwear products, comfort factors are also considered. The main reason is the relationship between comfort and performance. Given working conditions, the interaction of materials and product design with the human body corresponds to the physical and physiological side of comfort. In addition to these two aspects, there are psychological factors that shape the perception of comfort. If the user believes that the products do not provide adequate protection, this increases the levels of work stress. The management of mechanical phenomena has attracted the interest of major sports footwear manufacturers. In the field of therapeutic footwear, there is a considerable volume of documented research that study the effects of footwear design on the relief of plantar and other foot pressures. In the areas of work, military operations, sports and podiatry, comfort is important and the interest of researchers and professionals for comfortable footwear is significantly increased.
Physiology, psychology and physics of comfort. Mechanical support and anatomical elements of the foot are related to the transfer of forces from the ground to the human body.
The transfer of these forces and the ability of the extremity of the foot and the human body to receive these forces without damaging the tissues or pain is related to comfort. The foot feel capabilities are the second important aspect of foot comfort. In a higher animal organism like human, without psychological processes it is impossible to form a perception of phenomena. Assessing comfort or discomfort, that is, psychological comfort, is not simple, due to the subjectivity of the phenomena. The comfort of the foot is related to the functions of the senses and the homeostatic response to changes in the external and internal environment of the foot and the human body in general. The internal environment of the foot is affected by internal inflammations, injuries or conditions that alter the homeostatic balance or normal function of the foot. The main conditions of the external environment that affect human homeostasis are temperature, humidity as well as the structure and mechanical properties of the soil.
Specific performance requirements in engineering approach. The purpose of applying an engineering approach to any structure is to design and manufacture so as to meet specific performance requirements. When it comes to footwear, managing performance for every mechanical comfort aspect is becoming, eventually, a problem of managing geometry and material selection. There are two key approaches when examining product ideas that have to meet specific performance requirements.
The first approach is the examination of several ideas or prototypes and measuring, calculating, estimating or simulating performance. The second approach, which is practically feasible only through IT-based simulation tools, is optimization. In practice, the footwear designer may apply both methods. For example, the first approach to examine general design ideas, whereas the second one to fine-tune key design options.
Complete approaches to the issue of footwear comfort.
Much of the research on comfort-related stimuli on mechanical phenomena focuses on specific issues, for example, energy absorption. There are minimal integrated approaches to the overall treatment of shoe comfort. Brazil was the first country to develop national shoe comfort standards in 2002, which treat comfort as a multifaceted issue. The following aspects of mechanical comfort are well documented in scientific literature and have been modeled through differential and finite element methods.
Plantar pressure distribution and maxima, shock absorption and sole cushioning characteristics, bending characteristics of the sole structure,
Torsional characteristics of the sole structure. Fitting. Digital 3D foot biomodels. Medical models or biomodels are identical copies of the geometry and morphology of the human biological structure and are divided into two categories: computer-based biomodels and physical biomodels. Computer-based biomodels are divided into virtual biomodels that are used to display human tissues and implant design, and computational biomodels that are manufactured for the industrial analysis of biological structure. Models of this type are used in the finite element method to study the stress and strain of the human skeleton. Physical biomodels are manufactured using computer-aided manufacturing technologies, like CNC technology or rapid prototyping methods, from the corresponding computer-based biomodel. Biomodels are also distinguished in generic anatomy models and in individual anatomy models. Process of constructing digital 3D biomodels of human foot.
The process of constructing a 3D digital biomodel consists of 4 basic stages. Stage 1. Image acquisition. This step results in personalized images or sections with the method of computerized tomography or magnetic resonance imaging. Stage 2. Image processing. This step involves 2D segmentation to identify the areas of the image that identify the boundaries of each tissue. Stage 3. 3D reconstruction of the biomodel. This step relates to the 3D geometric modeling of the tissues. The final solid models are constructed after optimizing and smoothing. Stage 4. FEM model of the biomodel. In the final stage, all 3D models of anatomical details of the foot are inserted into a finite element system where FEM-messing is performed.
Finite element analysis, FEA, and footwear design. Plantar pressure. Shock absorption.
The foot sole system is usually charged by the weight of the person and the resistance of the ground and foot elements, simulating the gait phases. Kalaki et al. Investigated the effect of materials on the layers of the sole on plantar pressures. Linear elastic materials were used for their analyses. The upper part of the foot was fixed and a stepwise displacement was applied at the lower sole surface. By running the corresponding FEA analysis, the applied forces, reaction forces, and the plantar pressure distribution is calculated. The maximum plantar pressure decreases with decreasing sole stiffness. This decrease is almost constant for all gait positions.
Bending and torsion.
A study of sole bending using various footwear materials to find the bending behavior was performed by Papagiannis et al. 4 of the most usual footwear sole elastomer materials were selected for the analyses and linear mechanical properties were assumed for each trial. The structure is fixed on its lower front side and the back part of the structure is bent upwards by a max angle 55 degrees. Calculated values for both maximum principal stress and strain energy are higher for increased Young's modulus of the sole material, indicating a realistic approach to assessing bending deformation characteristics of footwear components. Torsion analysis can be conducted either by fixing the lower front part of the sole and rotating the heel part, or by fixing the heel part of the sole and rotating the front lower part. In the following example, the heel is fixed, and an anti-clockwise rotational deformation has been applied to the structure of the sole. Calculated values for both maximum principal stress and strain energy are higher for increased Young's modulus of the sole material, indicating a realistic approach to assessing torsion deformation characteristics of footwear components.